Good afternoon. So we are starting our second lab for this course, and in today's lab you'll be doing an exercise on actually designing a lens with a specific focal length, and you'll also be looking at how you trace rays through the system. So I want to give a brief talk a little before that so that you have some background that helps you carry out the lab exercises. Okay, so when you look at ray tracing, there are actually several ways you can trace rays through a system. Okay? So there are three different ways that are used predominantly. They're called the YNU technique or the YUI technique or the matrix method. The YNU is considered a very efficient method because the number of steps you take to trace any ray is less. The YUI uses one more equation, but because it does so, it gives you a little more information, and in fact that's what a program like OSLO does. It uses this technique, and the matrix method is slightly different approach to it, and we'll in fact spend some time in this course looking at matrix techniques for tracing a ray. If you think about it, you're tracing a ray through a system. That means at one point you know the height and angle a ray makes, and at one point that is at one interface, and then with that information and with any refractive index or curvature information, you then have to find a way to calculate what happens to this ray so that at the next interface you know what its height and what its angle are, what its slope is, and then you'll use this information and then find that for the next interface, and basically that is what you're doing when I say tracing a ray. Okay, so let's look at the YNU method just to give you an idea. Now, since we are dealing with paraxial optics, I can imagine that my optical surfaces are actually straight lines. I can make this assumption. Okay, so I'm going to consider every interface in my assumption of paraxial optics as a plane surface perpendicular to the optical axis. So if I have a ray that is incident here, and then this is an interface, so that means there's one refractive index on one side, let's say n, and on this side is n dash. So because of this change in refractive index, the ray bends, and let's say it travels to this interface here. Okay. So I know the height of the ray here. Okay, let's call this y minus 1 because it's the height at the surface previous to this surface. This is y, and of course the angle. Now how do I define this angle? I could define it with respect to different directions. I am going to define it with respect to the optical axis. So this line is parallel to the optical axis, so I am going to define it with respect to the optical axis, and I'll say this is u dash. Okay. Now the distance between these two surfaces or interfaces, let's say, has this value. So I know the height at one interface, I know the angle the ray makes with the optical axis just after the interface, and I want to find out the height at the next interface, right? So I am going to write this in terms of this angle, which is nothing but this height y minus the previous height divided by the thickness, or if I am writing it in terms of the new height, that's going to be nothing but the previous height plus this. Okay. So this is nothing but a kind of translation equation which tells you, if you know the height at one interface, given some information, you can find out the height at the next interface. Okay, so this is one equation. So this is the y of the y and u method. Okay. Okay. Now, what if I want to take the curved surface into account? What do I do then? Okay. So let's say I now look at my interface and say I want to take this curvature into account. So I'm going to look at this. Let's call this capital R. So this is a spherical surface of radius of curvature capital R, right? I can consider, so the thick black line is the ray. It's incident on the surface, and because of the difference in refractive indices, let's say this is n dash, the ray bends according to Snell's law. So I have, in fact, if I write Snell's law, I'll say n into the angle of incidence is equal to n dash into the angle after refraction. I'm leaving out the signs because I'm still considering these rays to be paraxial, and so theta is almost equal to sin theta. Okay. What is I? It's always the angle with respect to the normal. So that's this in this case and this in this case, because this is the center of curvature of this surface. Okay. So n is really theta plus u, it's n dash, which is theta plus u dash, but theta is nothing but y by r, right, the height of the ray, and I could just say y into the curvature. 1 by r is the curvature. So if I expand this, I have nyc plus nu is equal to n dash yc plus nu dash, right? And I can write this again just in terms of the angle after the interface, and that is going to be nu minus n dash, so let me write it in terms of yc first. Right? Okay. So this is a second equation that gets used for tracing rays through a system. Okay. And I could further simplify this because I recognize that this, in a sense, is the power of this interface, because it takes into account the refractive index difference on either side as well as the curvature of the surface. So I could in fact say, let's write this more simply as this, where phi represents the power of this surface. Okay. So this is another equation that I would use. Right. Okay. Now, OSLO will use a slightly different, use these equations. It also uses the simple equation of I is equal to, I have it over here, I is equal to theta plus u, or in other words, it uses the equation I is, theta was nothing but y by r plus u. So OSLO uses this equation for I, the equation for y, the equation for nu dash, and some form of yui or ynu is what OSLO uses to trace rays through the system. But you can clearly see that with these parameters, given the information at one plane, you are able to trace the ray through the system and then find out the slope of the ray as well as the height of the ray at the next interface, and then you'll calculate what happens at that interface, use those parameters as input and calculate what happens at the next interface, and so on. Okay, so that's basically how your ray tracing is going on. Okay, now if I look at in a little more detail, in OSLO, I said there are different ways of entering information. You could go into the software, into that spreadsheet, and you could manually enter values. So what are the values you're typically entering? You might be entering the radius of curvature, you might be entering distance, which they call thickness, you might be choosing a material, a glass type, and so on. But sometimes it's convenient for you if you are able to tell OSLO to calculate a value and say please assign the value for the curvature or for the thickness such that the ray does something specific. Okay. So, though the act of doing that is called using a solve in OSLO, and there are two solves that you will use very commonly. One is the angle solve, and you should recognize this equation. We just derived this now. So, what are you doing with the angle solve? You are saying I want the curvature of a surface to be or to have a certain value such that the ray that traverses it will have a certain angle. Okay. So, you are going to say this is the angle I wanted to have. In order for it to have this angle after this surface, what should the curvature of the surface be? Okay. So, rather than go to the column where you enter radius of curvature and enter directly a value of curvature, you will say choose the curvature, give me the value of curvature such that the ray has this angle afterwards. Why would you do that? You are going to do it in today's exercise, and I will give you one example of why you would do that. Let us say you have rays coming in from infinity. So, they are coming in from infinity and you want to choose the distance here. So, you want to choose this thickness, okay, such that this is equal to the focal length. Okay. However, if the rays are coming from infinity, I know that this angle here theta, it must be equal to this distance, let us call it d, or actually let us call this distance the full distance d. So, this is d by 2 by f, right. In other words, this is nothing but 1 by 2 of the f number of your system, right. Now, if the ray coming through, and I am not talking about any ray, I am talking about the axial ray, because the axial ray starts off from the object point that is on axis and focuses at the image point on axis. So, I am saying let the axial ray angle after this second interface be d by 2f, and in doing so I am choosing the focal length of the lens, right. So, that's the key to what I am doing. I am choosing the curvature such that I am actually choosing the focal length of the lens, right. If I changed the value of f, I said let it be, I calculate so that it is here, I am then saying what is the curvature for this new focal length of the lens, right. So, this is one place where I would use an angle solve. The other solve that is commonly used is the thickness solve, and again I am using an equation that we just derived. We are saying choose the thickness. So, maybe I have many interfaces, many optical interfaces in my system, and the ray is travelling through this, bends at each interface, it is continuous, right. And I am now saying I put a solve here, this plane, I put a solve and say choose this thickness, tell me what is thickness t, such that the height at this interface is equal to, let us say, 5 millimeters, right. I do not know where that height happens, but I am saying put the next interface wherever that height happens, right. And again, depending on what I want to do, I will say choose the axial ray height or choose the chief ray height. I can choose which ray I am working with, okay. 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 So, this is basically what we are going to be doing in today's lab class, and one of the things you will need to do is to go and pick operands that you want to work with. This will become clearer as you work out the exercise. I just wanted to show you this. I will also run through it in OSLO so it becomes clear. But this window shows you a bunch of operands that you can work with. And the first few operands, Py and Pu, are the axial ray height and the axial ray slope. And Pyc and Puc are the same parameters but for the chief ray. and the remainder, so you see it starts from something called PAC all the way to this total SPH. These are all different kinds of aberrations. So the first few are chromatic aberrations, and then SA3, these are the third order monochromatic aberrations, and then you have the fifth order monochromatic aberrations, and this last parameter here is actually the effective focal length. So the way we used PU, we calculated the U angle, right? We were in effect saying what should be the curvature so that I get a certain focal length. So in some cases I will use the PU operand in order to control or design a lens of a particular focal length. You could also use the effective focal length. We will learn what effective focal length means. So there are two operands we can use, and I'd like you, as we go along in this course, to try to understand why there are two operands and are they exactly equivalent, and if not, what are the differences. Okay, so keep that in mind. Go to OSLO. So if you open OSLO, you always of course get the startup option. We want to start a new lens, so that's what I'm going to do. And let me just enter something randomly. So let's say the first radius of curvature I take is 100, and I'm going to insert one more row. Let's make it a convex lens, so the next radius of curvature I'll make it negative -100. I want to see what happens at the image plane, so I am of course drawing the last surface. So we go to the last column, the special column, surface control, general, and say we want this surface to be drawn, always accepting inputs with this green tick mark. Of course there's nothing here yet. By clicking on this red set of lines, I'm getting all the aberration curves drawn, but the system isn't shown because although I've entered radii of curvature, I haven't yet entered any material. There are no interfaces yet in this. So I'm going to enter, as I said, BK7, which is a standard glass type. I still don't see anything very much. Now my lens is there, but the image plane is bang after the lens. I've not given any distance between image plane and the lens, and I've not given much, there's no field angle, there's no entrance beam radius. So a couple of things to note here. I would start by entering the beam radius of the beam size that I want to work with. So let's say we have a 3 millimeter radius beam, and this number indicates 0 for OSLO. This is a truly paraxial ray. There's no angle at all. Let's give it a small angle of 2 degrees. Okay. Now you should notice that when I change the entrance beam radius, by default OSLO will make the first surface always the aperture stop. So that's why you have this AS over here, right? And now you should understand what that aperture stop means. If I want, I can change. If I have a number of elements, I can pick some other element to be the aperture stop, but by default the first element is going to be the aperture stop. And you should notice that when I change the entrance beam radius, the radius of the aperture stop also changes, because, so let's say if I gave it 5 millimeters, this also changes to 5, right? Why is that happening? Because OSLO works on the principle that the entrance beam radius that you give, you say I want my beam to have this size. In other words, you want the beam that makes it through the system to have that size, and we now know that the element that controls what goes through the system is the aperture stop. So it is going to control the size of everything else such that this size beam goes through, and that's why when you enter it there, that's what gets changed at the aperture stop. Okay, I don't want such a large ray, so I'm going to go back to 3 millimeters. Okay. Okay. Let's also give the lens a finite thickness. It's not 0. Okay. So I see that thickness now, but of course I still haven't got my image plane moved away. My image plane is right after the lens because the thickness here is 0. Let's say I moved it some distance. Now I can see now the image plane has moved, but this is clearly no, I'm calling it image plane. In Oslo, that really means the last plane you're looking at. It does not necessarily mean that's the plane where the best image is formed. Okay, you might have to do something different in order to get to the plane where the best image is formed. And you can see very easily here, you're not at all near the plane where the best image is formed. We have a parallel beam coming in. The best image is, in this case, is definitely going to be formed at which plane? At the focal plane, right? So you can clearly see this is not near the focal plane. Now you don't yet understand all these aberration curves. All these other curves here are aberration curves. But if you look at them, you can see that the scales on these, just keep an eye on the scales. You have about 2 millimeters here, you have minus 100 to 100 in this scale. You have fairly large numbers. Now let's go to closer to the focal plane. And how will I know that? Well, I have the effective focal number listed up here. It gives me the effective focal number. It says 97 millimeters. So let's go to 97. Okay, and you can see these numbers have come down drastically. The aberration, this astigmatism was going from minus 100 to plus 100, and now it's minus 1 to plus 1. Right? This was 2 millimeters, and you see it's now 0.1 millimeters. So that's every time it's replotting this curve, it changes the scales to fit what are the values being generated. So don't just look at the shape of these curves, you also always need to keep in mind the scale or the values, right? And we'll anyway come to these curves later, but you can see even from this image that the image plane is now clearly closer to the focus. I entered a number very close to this effective focal length. I didn't actually enter the exact number. I'm now going to use a solve. So I will click on this little square button next to the thickness. I'm going to ask Oslo to solve for the thickness such that, so I'm choosing a solve. I'm interested in finding where perfect focus happens. So it's the axial ray that will have 0 height at perfect focus. So I'm going to pick axial ray height, but I want the plane at which the ray height is 0. I could pick the axial ray and say choose the plane where the height is some other value. I want the place where it's 0, where it crosses the axis. So if I do that, you can say it has picked a value 96.4, and if we go to the image now, it's really at the focus, and you see the scale values here, they've even come down, so the aberrations have decreased further, right? Because you are now at the perfect focal plane. Okay, do you have any idea why this focal length and this number here are not exactly the same? Because the lens has a certain thickness. Okay, and we will also, yeah, it's basically that. We'll go into that in a little more detail over the next few classes. Okay, I need not solve for axial ray height, right? I could solve for chief ray. So let's say I took chief ray height. Where will the chief ray height be 0? Where if I click 0 now, so now I'm saying solve for the thickness such that the next plane is the place where the chief ray height is 0. Where will that next plane happen? It will happen at the lens itself, because how did we define the chief ray? We said the chief ray goes through the center of the exit pupil, right? Does it? Yes, no? And what is the exit pupil in this case? You image anything that comes after the aperture stop, but here the lens is the aperture stop and there's nothing after the aperture stop. So the back of the lens is going to act as your exit pupil. So if you choose solve where the height is 0 for the chief ray, it is exactly at the aperture stop itself, which is the lens itself, right? So these are just tools that allow you to calculate thicknesses or curvatures, right? I can go here again, there's a solve here that says solve, and say solve for which ray? You're saying solve, give me the radius of curvature of this surface such that a ray has a certain angle after it, but I have to tell OSLO which ray to solve for. So you can see there are a number of rays that number of axial rays and a number of chief rays you can choose. If you choose that, you have to say what is the angle that I want, and then it will choose the curvature such that that happens. Okay. So these are some tools that will help you carry out today's exercise as well as the exercises in the future labs. Okay. So I think with that background, I will let you start the lab exercises. Please go through the first part of the exercise or what has been given to you in the PDF file, and then start working out the exercises.